Okay. Can we start? Okay. Yeah, thank you very much, Geray. Hello, everyone. Thank you for coming, for attending one more lecture of this course on computer architecture. And today, in lecture 10, we are going to discuss we are going to present a real-world PIM architecture, processing in memory architecture, and we are going to introduce you into how to program this architecture. This is important for you in this edition of the course because we are going to release a new lab that is about programming the real PIM system. So that's why we will put most of the focus today on how to program this architecture, even though we are going to describe as well the microarchitecture and the ISA of this PIM system, this PIM architecture, and we will also explain some of the work that we have done with it in our research. Feel free to ask any questions over the course of the lecture, and yeah, don't hesitate to express your doubts on or even your worries about the upcoming lab. So just to recap a little bit of what we have done in this course with respect to processing in memory, you may remember this was, if I'm not wrong, lectures 3 and 4, where we introduced processing in memory, motivating and justifying why computing systems need to be more data-centric or more memory-centric, and we explain or we introduce processing in memory as a paradigm that can alleviate the data movement bottleneck that exists in processor-centric systems. Remember as well that we covered and introduced 2 directions in processing in memory. It's a pretty simple distinction. One of the 2 directions uses the memory cells directly to perform computation, while the other direction is more, let's say, straightforward, because it basically proposes ways of placing compute elements, actual cores or accelerators or reconfigurable fabric, for example, as well, near the memory arrays. To conclude with these 2 lectures, we also discuss things that still need to be done to enable the adoption of processing in memory. And you may remember, well, some of the readings that we proposed, including this book chapter, where we summarize all these different challenges, some interesting proposals in the 2 directions, processing using memory and processing near memory, and also explain what are those challenges that still need to be fixed and solved in order to enable the adoption of processing in memory. Regarding the 2 PIM approaches, remember the distinction between processing using memory, and this might work or works indeed for many different memory technologies. Enabling technologies here are SRAM, DRAM, phase change memory, and also non-volatile memories such as PCM, but also MRAM, ReRAM, and restores, etc. And then processing near memory, where the compute units, the processing elements, are placed near the memory arrays, and there are different ways of implementing these. In fact, today we are going to focus on this approach because it's the first one that has become real, that has become available in the real world. In particular, we will be more or less in this enabling technology, logic in memory chips. As you will see, the UPMEM PIM architecture, that is the main focus of this lecture, places processing elements, small cores that near each of the DRAM banks. We talk a little bit about the UPMEM PIM architecture as well in the book chapter. It's this section 8.7 about real PIM hardware systems and prototypes, where we introduce the UPMEM PIM architecture, some of the research work that we have done with it until now, and also other real PIM architectures. Some of them you already know, indeed, because we introduced them in a previous lecture. PIM is becoming real as a paradigm that has the potential to alleviate the data movement bottleneck in processor-centric systems. And as you already know, the first company that started to commercialize a real processing in memory system was the French startup UPMEM. We have seen recent announcements from Samsung, for example, at the ISSCC 2021 conference. They announced in DRAM, that is also called, more frequently called these days, HBM-PIM, and later they also announced DIMM-based solutions. This year we had an announcement in February, also at ISSCC conference from SK Hynix. This is the first one of these architectures, the UPMEM-PIM architecture. You have already seen this slide. It's basically DDR4 DIMMs with typically 16 chips. In each of the chips, there are 8 DRAM memory banks, as you will see, and near each of the DRAM memory banks, there is a small processor that is called DRAM processing unit, or DPU. This is the picture of the dual socket system that we have used in our studies, where you can identify the 2 sockets, CPU 0 and CPU 1, and then a few DIMMs of DRAM that still are used as the main memory of the system, and then the PIM-enabled memory, those other yellow color DIMMs that you see on the screen, that are the PIM-enabled memory, and they behave as an accelerator in this computing system, as we are going to describe as well in this lecture. This is the announcement from Samsung related to the HBM-PIM architecture, an architecture that is focused on boosting the performance of artificial intelligence and machine learning workloads, and it's based on HBM2 memory. It's based on HBM2 memory. Remember that HBM is a 3D stack memory design, is DRAM. Each of the layers is a layer of DRAM memory. What Samsung did was modifying some of these layers in order to embed some cores, some small computing units that are called PCUs. Here in this slide, you can see the chip implementation, one of the layers where some of the DRAM banks are indicated here, and the PCU blocks in between of 2 DRAM banks. And this is the other proposal from Samsung. It's a DIMM-based solution. In this AX DIMM buffer, they will place a small FPGA, similar to the design that you can see there in the prototype, and they have tested this for recommendation systems. And this is the announcement from SK Hynix earlier this year, and this is the chip implementation of this AIM accelerator in memory with 16 processing units in each of the dies, as you see. In this case, I mean, it's a kind of similar design to the HBM-PIM thing, but instead of using HBM here, it's a GDDR6 memory. And instead of having 1 processing unit every 2 banks, here it's 1 per bank, as you can see. And here you can see a little bit more detail, and actually the detail of the processing unit with an array of multipliers and other tree. And also this supplementary SRAM buffer that I already mentioned in a previous lecture, that is useful to move data between different DRAM banks. This is another proposal also presented this year. This one is more application specific. As you see, there is a layer of DRAM and a logic layer or logic die, where there are some specialized units for certain operations in recommendation systems, this neural engine and match engine that you can see at the right-hand side of the slide. But today we are going to focus on the UPMEM-PIM architecture. The main reason for that is the one that is already accessible. The SDK is released. You can install it in your system. If you have a Linux machine, or even if you have a Windows machine or Mac, you can have a virtual machine, install their SDK. In the SDK, as you will see, there is a simulator. That's actually what you are going to use, at least for now, in your lab. It's not so straightforward to provide you with access to a server because there are not so many servers of this kind, and the simulator is more or less enough for you to have, let's say, the first approach on how to program these kind of systems to make sure that your code is functionally correct, and even have already some approach and some experience to the performance that you can obtain with the system, and how this performance can be optimized with different combinations of instructions, essentially by applying optimizations to your code. So all of that you're going to be able to learn in thanks to the lab. Yeah, so as you already know, we have worked on this architecture extensively already. We have written several papers. This one was the first one, and most of the lecture today is around the contents of this paper. It's a pretty long paper with many details, and yeah, most of the results that you're going to see, if not all the results that you're going to see, are in the paper. All the codes that we generated while developing this work are publicly available. They are in an open repository. This is also very good reference for you, not only for the lab that you will do, but also for future, if you keep working on this architecture, because maybe you will be interested in doing semester projects with us or master thesis at some point. This is a picture of some UPMEM DIMMs. This is the model E19. That was I think it was like the first prototype that they had. It only had 8 chips per DIMM, as you see, and the DPUs were relatively slow at a frequency of 267 megahertz. Later, they fabricated this newer generation with 16 chips per DIMM. There are 2 ranks of 8 chips, each of them, and the DPUs run at a little bit higher frequency, 350 megahertz. That number corresponds to the version that we used when we did all the research work that we are going to present today. Nowadays, these DPUs run at a little bit higher frequency, 425 megahertz, and I think that UPMEM is working on enabling a little bit higher frequency, something like 500 megahertz, or maybe even a little bit more. But yeah, in the end, let's say that this raw frequency is important when you want to compare the system to other devices, other accelerators or general purpose architectures. It's not so important when it comes to understanding the architecture itself, or what different programming decisions might, the performance that different programming decisions might produce. So in the end, what counts is the number of cycles that you spend, right? When optimizing code for a specific machine. You already know what are the promises of processing in memory. In the end, what we try is to alleviate the data movement bottleneck, in some way avoiding so much data movement between the memory units and the compute units. That is going to save execution time, execution cycles for sure, because we don't need to move the data from here to there. And also is going to save a lot of energy. This slide is from UPMEM. Actually, they used this in the presentation at Hot Chips 31 in 2019. And to me, one thing that is interesting to observe, because also is related to some of the numbers and figures you have already seen in this course, is the large difference between operating the data, operating on the data in the processor, or operating on the data near the memory, right? So here you can see sort of raw comparison of the energy that is needed to move a 64-bit operand from DRAM to the processor. To the processor, meaning either the CPU or one of the DPUs that reside near the memory. So in the case of the UPMEM system, this is the value, while in the case of a normal server where you need to move this 64-bit operand from the memory unit or from the memory bank to the CPU is way higher, right? You can compare these two numbers as well with those motivational numbers that we showed you in earlier lectures, and you'll see that more or less they are in the same ballpark, right? In the same order of magnitude. So that's expectedly one of the key advantages of a processing in memory system, that we can save a lot of energy as well because we don't need to bring the data to the processor. However, it's not that easy, right, to design a processing in memory system, and we indeed mentioned some of the challenges in an earlier lecture. Remember that the paradigm itself, the idea of processing near the memory or in the memory is relatively old. It's pretty old. It's like 50 years old at least, but back then it wasn't easy to implement real systems, right? Because of some technology challenges, different type of processor, different type of transistors that are used in CMOS process or in DRAM process, different number of metal layers as well. And the number of metal layers in DRAM technology is way smaller than in CMOS technology, and that makes, as you see, 3 metal layers only for routing, and that makes way more challenging to design the processor itself, the DPUs in this case, using the DRAM technology. But still, they figure out ways of doing it in a efficient way, or more or less efficient way. They had to make strong design choices, but yeah, in the end, they were able to design a processor that is more or less capable to do useful work near the memory and also do it in an efficient way. We will see some of the, some of these design choices over the course of the lecture, such as, for example, how many pipeline stages, why relatively deep pipeline of 14 stages. It's all about taking advantage of the relatively low frequency that they can have inside the memory. If you want to know what the UPMEM system is, there's a first definition. It's a memory circuit with a memory array, a DRAM bank, and a first processor. This first processor is called first processor here because it's the one closest to the memory array. This is the DPU. And there is a control interface for the first processor to receive commands from a central processor that is going to be the host CPU. And these memory banks become accessible either to the central processor or to the first processor. So basically, the system or the chips are designed in a way that are either the DPUs inside the chip that are working with the data that resides in the memory array, or the host CPU is accessing that data in order to either write new data or read some results, right? We are going to discuss all of this with a lot more detail. Any questions so far? Or in YouTube, maybe? Yes. What is the routing density? So when you design a chip, you need some lines, right? Like metal wires to connect different components, right? So the routing density is how many of these wires you can have given a certain amount of area. Higher density means more of these lines, and that means that you can also afford a more complex design. Okay? Any other question? Okay, so this is more or less the outline of the entire lecture. We will put most of the effort in the beginning because I want you to very clearly understand how the system, what's the system, what parts it has, and how you need to think about it. And then we are going to focus for a few slides on how to program, right? Because that's going to be your main task in the upcoming lab. After that, we are going to go into some details about the DRAM processing units themselves so that you know a little bit more about the microarchitecture and the ISA, and also start understanding what are the performance limits of this architecture. You will see that, well, even though each of the DPUs individually is relatively weak, but the whole system with more than 2,500 of these DPUs can be pretty powerful. And then we will describe and evaluate some workloads that are potentially suitable for this architecture. We have implemented and evaluated them, and we have analyzed their performance and compared their performance as well to CPU and GPU. The idea or the key goal of doing that is that we want to understand what type of workloads, what type of compute patterns are more suitable for this specific PIM architecture. It doesn't mean that if something doesn't look good today, it's not going to be a good use case for other PIM architectures or for PIM architectures in general, right? It's only that we use these workloads that we initially expected them to be good for this system. We evaluated them and indeed identified which ones are good and which ones are not so good. Why is that important? Because that also allows us to propose ways to provide recommendations about how to improve future processing in memory systems. So that's why I believe it's pretty interesting to work with this architecture, even though there is, as you will see, a lot of room for improvement, and that's good. It is already pretty good. And think about the fact that this is the first version of this architecture and is the first architecture that is publicly available. Okay, so let's start with the introduction. We are going to describe what we mean by the accelerator model, and after that, we will see the overview of the overall overview of the UPMEM-based PIM system. We say that this UPMEM-based PIM system follows the accelerator model because here the UPMEM DIMMs, the PIM-enabled memory, coexist with conventional DIMMs. They are still the standard main memory. So the integration of these DIMMs is as a coprocessor or an accelerator that works for the host processor or the central processing unit, right? The UPMEM DIMMs as well can be seen as a loosely coupled accelerator, and what that means is that we need to explicitly move data from the main memory to the accelerator, and then we have to explicitly launch kernels for the execution on the UPMEM processors on the memory side, right? So as you see, it's a relatively coarse-grained approach, right? Because we are offloading entire kernels where we will likely operate on many megabytes or gigabytes of data, and we perform as many operations as we can or as we should on that data. Right? It's completely different to, let's say, instruction-based approach as some of the proposals we have seen here. PIM-enabled instructions, remember that was one of the first processing near memory proposals that we covered in the corresponding lecture. In PIM-enabled instructions, we are offloading a single instruction to the PCUs, to the processing elements near the memory. A single instruction, this instruction gets executed on a single cache line and then returns the control or eventually synchronizes using a fence with the CPU threads that are running on the host CPU, right? Here it's different. Here we are offloading much more computation. In that sense, it's coarser grain is more similar to how we program GPUs as well. In GPUs, we typically offload to the GPU an entire kernel that operates on many megabytes or even gigabytes of data. And indeed, this way of using the UPMEM system resembles GPU computing, exactly because of the same reason, right? In GPU computing, if we are using discrete GPUs, we move data from the CPU memory to the GPU memory, then compute, and then return the results to the CPU memory. So that's what we are doing here. And it's indeed what the patent from UPMEM describes. First of all, the system on a chip, that here is the CPU, the host CPU, loads data to be processed to the DRAM memory bank. Then this host CPU transmit data processing command to the DRAM processors, to the DPUs. Then the kernel starts the execution, or the DPUs start executing the kernel. The kernel is the function that runs on the DPUs, data processing by DRAM processors. And right after that, right after launching the kernel, the CPU starts polling the state of the memory. It's checking with memory if data processing is complete. And when data processing is complete, the DPUs become idle, let's say, they stop computing, and the memory bank becomes accessible to the host CPU. So this is how it works. After becoming accessible, you can, the CPU can read the results, okay? And maybe redistribute them over the DPUs again for later computation for another kernel, or maybe complete the execution in the CPU using its registers and cache and so on. How is the system organized? Well, you have more or less seen similar picture to this one. This is the host processor with its own memory, and also this interface, or this memory bus to access the DRAM, both DRAM DIMMs and PIM-enabled DIMMs as well, right? Inside each of the PIM-enabled DIMMs, we have multiple chips. In each chip, we have memory arrays and we have processors. And here is essentially the same picture, but with a different style, right? You see the host CPU. The host CPU has one or more memory controller, one or more memory channel. Connected to these memory channels, we have multiple DIMMs. Some of these DIMMs correspond to conventional DDR memory, for example, DDR4, that are the main memory, and then we have the UPMEM DIMMs, the PIM-enabled memory. We can take a closer look at the UPMEM DIMMs. We have 16 chips in the newer generation, and inside each of the chips, we have 8 64 megabyte DRAM banks that are called Mram banks in this architecture, but they are DRAM. And near each of the banks, we have one DPU. So in total, we have 8 DPUs. We have 64 DPUs per rank, right? The way that each DPU uses the data in its memory bank is completely independent of other DPUs. This DPU here can access the data in this Mram bank, but cannot access data directly in other Mram banks. That's one characteristic of this system that is good that you understand as soon as possible. Yeah, well, as for a first description of what you can see here in the DPU, as you see, there is a DMA engine. This DMA engine can either move operands between Mram and this WRAM here, operands, data, or instructions to this IRAM, that is an instruction memory. It's an instruction memory. It's not an instruction cache, right? You know that instruction caches have some cached instructions from a program that resides in the external memory. It's not the case here. The entire program resides here in these 24 kilobytes of IRAM. And this WRAM has a size of 64 kilobytes. Of course, the size of these different memory spaces may change in future systems, right? These two are not DRAM, these two are SRAM. And then we have the pipeline. It's a little bit more complex than the basic pipeline that we start always explaining in computer architecture with, for example, 5 pipeline stages. But basically, you can identify a typical pipeline stages to access instructions or to fetch instructions, to read operands from the register file, ALU instructions to actually compute the arithmetic operations, for example, and then some final stages to write back to registers and and so on. So that's more or less the thing. We are going to go back again later over the pipeline, and we will describe it with a little bit more detail, but for you to become familiar with the pictures as soon as possible as well. This is the, let's say, largest UPMEM pin system at the moment with 20 UPMEM teams, because each of them has 2 ranks. In total, there are 40 ranks, okay? Remember, in each rank, there are 8 chips. In each chip, there are 8 DPUs. That means that one rank has 64 DPUs and 64 MRAM banks. Yeah, and here you have a little bit more detail about the dual socket system. In total, a maximum of 2,560 DPUs and a maximum of 160 gigabytes of PIM-enabled memory. The size of the total size of all the MRAM banks. As you can see, one good characteristic of this system is that it has a lot of PIM-enabled memory, right? So even though you need to move data from the main memory to the PIM-enabled memory before starting the computation, this data can potentially reside for a long time in the PIM-enabled memory, because there is a large amount of PIM-enabled memory, and yeah, that is potentially one of the strengths of the system. That this pretty large memory, especially if you compare to the typical memory sizes of other accelerators like GPUs or FPGAs, typically have smaller memories. And this is again the picture of the entire system that you're already familiar with. Any questions about this introduction? Yes? You could potentially have both in the system and run the workloads wherever you consider that they are going to be faster or more energy efficient or something else. But you can also see them as alternatives, right? You may have some workloads that you run in your system and your CPU, and now you want to accelerate this workload. This is an accelerator. The GPU is an accelerator as well. My recommendation would be that you choose the one that provides best value for cost, no? Performance and cost of the system might also be a good reason. So performance-wise, I'm going to show you some results here, comparison to CPU and GPU, and that I don't want to anticipate. Okay. So there are many different, but now that you asked, I would like to make the clarification. Regardless of what's the comparison, I believe that studying and understanding these kind of processing in memory systems is pretty good, because many of us have cars and need cars, but not all of us need or have money for a Ferrari, right? So that's one of the things to take into account when you compare different sort of accelerators. So that's one thing. Another thing that you have to take into account when observing this sort of comparison is that CPUs and GPUs have existed for decades. Their hardware is very optimized, their architecture, software for them is super optimized, while a direct comparison now at this point is comparing a super optimized system with something that is just starting. The question that you ask is like very reasonable. Everyone asks this question, but at this point, the comparison is not for us to decide, oh, I will go for this or I will go for that. It's more to understand what's the potential of the system that we are studying and analyzing. How far are we from the target? Let's say the target is the most powerful GPU that you can find in the system, in the market, for example, right? So that's why we indeed compare to CPUs and GPUs, other than the possibility of choosing between one accelerator or a different one. Okay. I disagree on that because both CPUs, CPUs, GPUs, and DPUs for this particular PIN system, PIN cores in this particular PIN system are general purpose. You can potentially write any code. If performance is not great, maybe it's because it's not the most suitable device, but they are general purpose. It's true that GPUs back in the 80s, they appeared and were designed for graphics, but today they are general purpose processors. And that's why we use them for many other workloads in HPC, machine learning, or any other domain.
But isn't DPUs on the PC design itself not only to be a general purpose, but to mitigate the problem of like data movement and energy consumption? So it's like a trade-off in your system. Perhaps you don't need too much performance, but you are much more in economy and energy. You don't want to mitigate the movement that you do with GPUs on CPU. And then let's say you have a kind of a workload that is very completely bound in GPUs, and you don't have to do a lot of data movement, and you don't need too much performance, and then you got that because of the energy system. And I think like this kind of system, GPUs will be like, is one of the idea why people are designing this. This is what I had in mind when I say that designing the system to different proposals, even though both of them are general proposals.
Yeah, well, I mean, yeah, what you're saying makes sense, but again, the purpose of this lecture, the lab, and actually your research is to understand what's the potential of this new system. In the end, I'm pretty sure. Well, I'm not so sure, but maybe in a few years and with more time, it will be very clear what's the right choice, right? I think that it doesn't make sense to compare processing in memory and GPUs directly. Maybe this kind of system, yes, because the PIM system, the PIM-enabled memory can be seen as an external accelerator, and you have to move data there. So in that sense, and that's something that I said earlier, is similar to the model for GPUs, but the concept of processing in memory is applicable to CPUs, GPUs, or other type of devices. We are not comparing. I mean, it's more like comparing a paradigm to a specific device. If you go a few slides back and see Samsung and SK Hynix proposals, HBM, PIM, and AIM, they look a lot designed for GPUs. And one reason for that is that HBM2 and GDDR6 memories are the memories that memory technologies that you can typically find in GPU design these days. So, but yeah, let's continue with the lecture, understanding the system, and hopefully by the end of the lecture, we will understand better what are the type of workloads that can be suitable for this specific processing in memory system, and also we can discuss things that could be improved in order to make it more suitable for other type of workloads as well. Okay, let's start with UPMEM PIM programming. And our first example is vector addition. We are going to start simple. In vector addition, as you know, we perform the element-wise addition of two vectors, A and B, and we store the results in another vector, the output vector C. The way that we compute this on a sequential CPU is by going one by one over the elements of A and B, performing an addition and storing in C. That's a sequential code. If you have a parallel processor, maybe a multi-core CPU or maybe a GPU, you can have multiple threads performing all these operations in parallel, because this is completely parallelizable and vectorizable code. Even the sequential loop can be parallelized and vectorized. So you can take advantage of that in parallel processors, including the DPUs. So what we do here is partitioning the workload over the different DPUs that we have in the system. Here in our example, we are using 4 DPUs. And then inside each of the DPUs, we have software threads that are running. The DPUs, as you will see, are a multi-threaded processor. They can run up to 24 threads, and they are there to fill the pipeline with their instructions and operate on part of the data that was assigned to the corresponding DPU. So, for example, thread 0 works on calculating these two elements, and thread 1 works on calculating these two elements. These threads are called tasklets in UPMEM terminology, but you can call them software threads if you prefer so, or pin threads, or whatever you prefer. And we would do similar distribution of the work in other DPUs. So as you can see, the indices of the tasklets or the pin threads are repeated from DPU to DPU. So here we have tasklet 0, tasklet 1. Here we have tasklet 0, tasklet 1. So if you think about it, if you think about how you will write code for these tasklets, this tasklet 0 is tasklet 0, regardless of what's the DPU that it's running on. And this tasklet 1 is tasklet 1. So in the end, we are writing code for one DPU, and this code is going to run on multiple DPUs by handling the pointers and parts of the buffers that are transferred to either this DPU or either this CPU and so on. We will have all of them working on different parts of the input, right? And calculating different parts of the outputs. Okay, yes. Yes. Yeah, we are going to talk about that. Yeah, that's possible. Different DPUs can do different things. Different tasklets can also do different things. And as you will see, they can synchronize, they can communicate. Remember that each DPU has an SRAM memory that is called Wram for operands. This SRAM memory is accessible by all tasklets. And there they can handle, they can keep their own private data, or they can also keep shared data that is accessible by all the different tasklets. So we will see how to do that. By the way, I will try, or I'm trying to provide you with enough information in this lecture to do your lab and learn how to program this system. But for sure, the best resource, or one of the best resources that you can access, is the user manual itself, right? The UPMEM SDK documentation, where they describe how to allocate DPUs, how to load programs into them, how to transfer data to the DPUs, how to launch kernels, etc., etc. So all of that is explained here, even though we are going to introduce everything in this lecture, or everything that you need to know for the lab. General programming recommendations. It's good to have something for a start, right? Because otherwise it's going to be more difficult to find what's the right configuration, or that's the right distribution of workload. So it's pretty useful to have some general programming recommendations from the beginning. For example, the first one: execute on the DRAM processing units portions of parallel code that are as long as possible. And that's, I think that it's a recommendation that it naturally makes sense. Why is that? Because we are offloading kernels for execution on the memory side, on the DPUs. But before doing that, we have to transfer data, right? We have to transfer data from the main memory to the PIM-enabled memory. And this happens through the CPU, indeed. It happens through the memory, conventional memory channels or memory buses. We know that the source, or one of the key reasons for the data movement bottleneck, is that we have to move data through these memory buses, right? So we want to minimize the amount of data that we transfer over these memory buses in the UPMEM system, or the other way around. Regardless of how much data we are moving from the main memory to the PIM-enabled memory, we want to compute as much as possible on the PIM-enabled memory, because that will mean that the fraction of time that is spent on the DPUs is longer than the fraction of time that we spend transferring data, right? So I think this is kind of intuitive. In this particular PIM architecture where we are offloading entire kernels, right? Long functions that operate on megabytes and may perform many different operations on the data that they have in the MRAM, right? So I think that this is pretty intuitive for the PIN system that we are working on. Also, it's necessary, or it's desirable at least, to split the workload into independent data blocks, which the DPUs operate on independently. That is going to be probably one key characteristic of workloads that are suitable for this PIM architecture. Vector addition. We can partition the vectors and operate completely independently on each of the different parts, right? So that's something that makes sense. This doesn't mean that you cannot implement a workload that requires communication between DPUs. No, that's also something that you can implement. But of course, that will have some overheads, and you will see why soon. Operate on as many working DPUs in the system as possible. Same thing as if you have a multi-core CPU or you have a powerful GPU with multiple GPU cores and you want to obtain the maximum performance in your system, right? And the last recommendation is to launch at least 11 tasklets or software threads per DPU. This one is not so intuitive, right? But we will see the intuition later because we were able to, with our analysis, we were able to figure out why this recommendation makes sense. Okay, so let's start allocating the DPUs. You have your CPU, you're running your CPU code here, you have DRAM, you have a PIM-enabled memory, and at some point, your program decides that it's a good time to offload something to the PIM-enabled memory because it's an accelerator, it can be faster, or it can be more energy efficient, and so on. We know already that the first thing we have to do is moving data, input data, the two vectors A and B, from the standard name memory to the PIM-enabled memory, right? That's conceptually what makes sense in the flow of the program. But even before that, we have to allocate, we have to tell the runtime, and we have to tell the admin driver to reserve some of the DPUs in the system for our program. In the CPU, there are multiple processes running, right? And our program is just one of those processes. There might be other processes that also need to use DPUs or want to use DPUs, right? In some cases, we may want to use all DPUs in the system because we want to go for peak performance and because we have to operate on very large amount of data, but in some other cases, maybe we don't have to operate on so much data and it's still worth offloading to the memory side, right? So that's why we have to allocate the number of DPUs that we want in our program. This DPU allocation is done by the host. So it's done in the code that we run on the CPU. And it looks like this. Observe that we are using C. We can also use C++ here. And the key difference between what you are going to see as pieces or code segments in these slides are only the specific APIs that you need to use to actually, in this case, make use of the system, right? And make use of this allocation, right? The API that we use to allocate DPUs for our program or to reserve DPUs that will work for our program is this one, is this DPU alloc. We allocate the number of DPUs, this NR underscore DPUs is the number of DPUs that we want to allocate. This is something that can be done, I mean, these NR DPUs can be, so could be provided at compile time or also at runtime. And as you see, the last parameter is the address of this DPU set. The DPU set is just an identifier of the set of DPUs that you allocate for your program using DPU alloc. And indeed, you can later double check that you allocated or the runtime system allocated the actual number of DPUs that you wanted, right? This DPU set, we can get the number of DPUs or in this DPU set and store it or move that value to this NR of DPUs and print it, right? I may want to allocate 1 DPU, I may want to allocate 100 DPUs, I may want to allocate 2,000 DPUs, right? That depends on the needs of the program. At the same time, can we allocate different DPU sets over the course of a program? Yes, we can. And we are going to see one example in the next slide. It might make sense that depending on what's the computation or how the computation evolves over the course of the program, it might make sense to use more or less DPUs in our program, right? Of course, at least at the end of the program, we will have to deallocate the DPU set using DPU free. But this, you can see it in a similar way as you use malloc and free to allocate memory in a conventional system. But in this case, you're allocating DPUs and freeing them. And this is an example of the DPU allocation that might change over the course of the program. In particular, this code corresponds to Needleman-Wunsch. I think you are familiar with Needleman-Wunsch already because you have taken a lecture about bioinformatics and sequence alignment. Needleman-Wunsch is one of the traditional algorithms for sequence alignment. And in Needleman-Wunsch, same as in Smith-Waterman and other sequence alignment algorithms, what we do is a dynamic programming algorithm, right? And what we do is computing a wavefront in multiple iterations. This wavefront is the anti-diagonal, right? And the size of the anti-diagonal is different in different iterations, right? And because of that, we need more or less computing resources to compute the values in each anti-diagonal. So based on that, we will also need more or less DPUs in the system as the computation of the dynamic programming matrix proceeds. Make sense? So that's why in each iteration of this code, of this Needleman-Wunsch, we free the DPU set that was previously allocated, and we allocate a new DPU set for the number of elements that we have to compute in the anti-diagonal, in each anti-diagonal in this Needleman-Wunsch. So that's more or less what we are doing here, just as an example of using different DPU sets of different size over the course of the execution. Okay, now, yes. For this specific algorithm, yeah, we are going to see some results at the end. And also, I think it's indeed a good question because there might be other ways of implementing Needleman-Wunsch, is what I wanted to say. Depending on, for example, you are very familiar with this, right? Depending, for example, what's the length of the reads. If your reads are short reads, you may not need to use more than one DPU for the entire thing, or maybe not more than even one tasklet, right? In this specific code that actually this belongs to our benchmark suite, we wanted to evaluate this kind of characteristic, this kind of features, right? Possibility of changing the granularity of the computation over the program. But yeah, that's it's really good that you are thinking along those lines. Okay, yeah, so now we have the DPU set is allocated, or program has access to a number of DPUs and the corresponding memory banks. So now what we have to do next is to load the program, the kernel that will run in each of the DPUs. And to do so, we use this DPU load. So DPU load loads a binary that is previously compiled, and this DPU binary is there in that path that you find there, you see there, and we allocate this binary on all DPUs of this DPU set. So that's how we move the program of a size up to 24 kilobytes from the main memory of the CPU, this program from our CPU, to each of the DPUs, and in particular to the instruction RAM of each DPU. Okay? Yes, yeah, here you are. Is it possible to launch different kernels onto different DPUs? Yes, it is possible. And that's something that you asked earlier, right? You can reserve different 2 DPU sets or more at the same, in the same program, and then load different programs on different DPU sets. That could be inside the same program, inside the same process, or 2 completely different processes running on the same system, right? And if you think about it as well, it's kind of an advantage of this sort of configuration. Why is that? Because different processes that may be using DPUs in the system are completely isolated from each other in the memory side, in the DPU side, because they are using completely different DPUs, and each DPU can only access their own memory, their own MRAM bank, right? So it's kind of a security guarantee in this case. So yeah, that's the thing, right? We can launch different kernels onto different DPUs. This can be useful for different purposes, for example, workloads with task level parallelism, or for example, different programs using different DPU sets. Okay? Okay, now a tricky part, data movement between the CPU and the DPUs. These are important, first of all, because we have to move the input data from the main memory to the PIM-enabled memory, and then we will have to move the results when the kernel terminates from the PIM-enabled memory to the main memory, right? But not only for that, we might also need to use these data transfers for communication across DPUs. For whatever reason, my program might need that I move data from this PIN chip or from an MRAM bank in this PIN chip to an MRAM bank in this PIN chip or in a PIN chip in another DIMM. I'll always have to do that through the main memory back and forth, right? So now you can, as you can imagine, that's going to be an important overhead for those workloads that require a lot of communication of this type. Anyway, terminology. This is what we call a CPU to DPU copy. You could use a different name if you want. We decided to use CPU to DPU. I think it's pretty clear what it means. And this is a DPU to CPU data movement or memory transfer. You will see that the SDK contains different ways of doing these data transfers, different APIs for different types of data transfers, and you are going to experiment with them in your lab. The first type is the serial CPU-DPU or DPU-CPU transfers. Here, we are only targeting a single DPU. We are copying data from the main memory to the PIM-enabled memory. If we use, yes. It depends on the workload. The point is to amortize the amount of computation that you, to amortize data movement with the amount of computation that you do in the PIM-enabled memory. And it depends as well on what's the size of the data that you're using. So in principle, if you are going to copy, let's say 100 megabytes of data or 1 gigabyte of data or even more, right? From the main memory to the PIM-enabled memory, that's a pretty large amount of data, right? And that probably will take a few milliseconds to copy, right? And if you're going to copy all that amount of data for just a single addition, element-wise addition, maybe it's not worth it, right? That's why one general recommendation is to use as much computation as possible. After you move the data, you keep computing here as much as you can. And this way, you don't need to, you amortize the cost of the data movement. There are many algorithms that are like that. For example, you can think about machine learning training. In machine learning training, we typically use very large data sets to train specific models, regardless of what's the algorithm or what's the type of machine learning approach. Very large data sets that can potentially and likely indeed fit into these 160 gigabytes of data. You just transfer that once, and then you compute pretty quickly with very little data movement over multiple iterations. That's one advantage. Now think about what's the typical size of caches that you have in the host CPU, and what would happen if you train using those 100 gigabytes that you can fit here. You train them using this, you train the algorithm or the method using only the CPU. It's 100 gigabytes that may reside in the, may fit in the main memory, but they don't fit in the cache. So in every iteration, you will have to go over all the 100 megabytes from main memory to the CPU, then from the CPU to the main memory, back and forth, maybe for hundreds or thousands of iterations. You see? So even though there is data movement, we are moving the data, potentially at least, in a smarter way. Okay? Okay, so different types of transfers, serial CPU, DPU transfers. Here you target a single DPU. So if you use serial transfers and you want to transfer data to all DPUs in your DPU set, this will go one by one. DPU 0, DPU 1, DPU 2, etc. Right? So the total time for these transfers increases linearly with the number of DPUs that you're targeting. Then we also have parallel CPU, DPU, and DPU, CPU transfer. In this case, we target multiple DPUs and multiple Mram banks. So what that means is that we can transfer one buffer to multiple DPUs or different buffers to multiple DPUs and do it at the same time. The key advantage of that is that we are going to exploit much higher bandwidth in these data transfers, right? So the data transfers will take shorter time in the overall execution. And finally, we have broadcast CPU, DPU transfers. Observe that these are not DPU, CPU. These are only in one single direction. And in this case, we are targeting multiple DPUs and multiple Mram banks, but a single buffer. That's why we call it broadcast, because it's this data, same data to all Mram banks. Okay? So what are the APIs for serial transfers? As you see, they have a pretty intuitive name, DPU copy to, DPU copy from. And this is how the syntax more or less looks like. It's this is here indeed we have two different transfers because these transfers correspond to the vector addition example that is our running example in this lecture, right? And here in the DPU set, we go DPU by DPU and we transfer a buffer either from an array called buffer A that is in main memory or buffer B that is also in main memory. We transfer something of this size. Input size, DPU 8 bytes times size of T, being T, the element, the data type of the array that we are transferring. Okay? So first of all, we also have to say what address in the DRAM banks, in the Mram banks, we are going to write. And what we typically use for these transfers is this symbolic name, DPU Mram heap pointer name, that defines, you can see just as a pointer, just an address to the start of the Mram range that can be freely accessed by applications. Okay? And observe as well that we don't allocate Mram explicitly. There is no malloc to allocate an array or a vector or a matrix in the Mram. We directly operate with the physical memory and with the physical addresses. So we do not allocate Mram explicitly. We only say, where do we start counting? And then where, I mean, and then what's the offset within Mram? So for example, this buffer A, or this particular address and this size, so this buffer of a certain size is going to be copied to the beginning of the Mram because the offset is 0 in each DPU that you target, this DPU here, okay? The second one, in this case is buffer B, is going to be copied somewhere later, right? And this is the offset. You can see that this offset for buffer B is exactly the same size as the size of the buffer from A that we copied into this MRAM. So basically what we are doing is from the start of the MRAM, we copy a few bytes from array A or from buffer A, and then we copy a few bytes from buffer B. And this is how it works, okay? Yeah, these copies are, okay, so I know what you're asking that, right? You're asking that because you want to know if it's possible to launch DPU kernel. So in that sense, they are synchronous, right? We are not going to launch a kernel until the transfer has happened. However, as we are going to see next, the DPU kernel launch can be synchronous or asynchronous. So you could start one of these transfers to other DPU different to the ones that where you are offloading a specific code. But yeah, that's it's good that you think along those lines. It's a good question. Okay, this is the pointer to main memory, right? Buffer B and buffer A and buffer B, as I said, and this is the transfer size. Okay. Okay, so now parallel transfers. We push different buffers from a DPU set in one transfer. All buffers need to be of the same size. If for whatever reason you have different sizes of these buffers, you cannot use parallel transfers, at least with the current SDK. This is not an inherent limitation of the system or a fundamental limitation of processing in memory, not at all. It's just a limitation of the current runtime system and the current SDK. We first need to prepare the transfer, then we push. Push means that we execute the transfer, basically. And we have to define what's the direction, either to the DPU or from the DPUs. And this is how the code looks. Here again, you have buffer A and buffer B, but now we are using parallel transfers. But again, for the DPU set, we prepare the transfers for all DPUs, right? And indeed, we do it one by one. We first need to prepare the transfer, then we push the transfer. You see, this is for buffer A, this is for buffer B. We need to use, when we prepare the transfer, we need to use the pointer to main memory. You can compare this pointer to the one that you have in the previous slide. You will see it's the same one for each DPU. This I here indeed represents the DPU ID from the host perspective. So we are transferring a different buffer to each DPU, right? But the way that we perform this transfer is essentially the same. The only thing that changes is the pointer, right? Remember that the parallel transfers need to have a fixed size, the same size for all buffers. So that's why we don't say what's the buffer size here. We say what's the buffer size here in the second line in the push transfer because it's the same size for all DPUs. And here we see the direction, right? In this case, because these are the input buffers, A and B, we transfer to the DPU. And again, we have the offset within MRAM where we are going to write the specific buffer, either A or B, the transfer size, and yeah, there is another parameter that we don't have to describe now. Okay? Okay, and finally, broadcast transfers. DPU broadcasts, DPU broadcast 2, only from CPU to DPU. We transfer the same buffer to all DPUs in the DPU set. That's why we have one single pointer to main memory for the whole DPU set, okay? And it has a certain size. So this is the broadcast transfer. Can we have different types of transfers in a program? Yeah, right, makes sense, right? So if we have to broadcast data because let's say one vector in an implementation of matrix vector multiplication where you, for example, distribute the rows of the matrix, the rows of the matrix over multiple DPUs, but then you want to perform the dot product, the row by vector multiplication in each of the DPUs, you'll have to transfer the whole vector to all DPUs, right? In that case, it makes sense to use a broadcast transfer, right? Because it's just a single line and you transfer the vector to all DPUs. In other cases, you cannot do that because the part of buffer A and the part of buffer B, as in vector addition, is completely different for different DPUs. So it makes no sense to use broadcast transfers there, but you can use parallel transfers because all buffers can be of the same size. But then there will be also cases where the buffers are not of the same size. And this is when there is, for example, some computation that is data dependent. Here you can see one example is a database operator called select. In select, what we typically do is filtering some elements in an input array. We remove, in this example, we remove even values. So we have to check with a predicate if each of these values is even or not, 2, 1, 3, etc. And yeah, for the whole array that may have many gigabytes, we partition it over the different DPUs that we have in the system, equally sized chunks to each of the DPUs. But then, because the distribution of data is not the same for all DPUs, as you can see, the number of elements that they filter is different, right? And that's why the output might have different sizes in different DPUs. And in this case, we would need to use serial transfers to move the results from the DPUs to the main memory of the CPU, right? Now, one question is, oh, maybe I could use padding and then here transfer 2 instead of just 1 for DPU 2. Yes, of course, you can do that. And that's probably a practice that is going to provide a little bit more performance to your code. Of course, it's more complex. It will be more complex to do because later in the CPU, you might need to compact or do some other things. But yeah, those potential optimizations are possible and probably beneficial for many different workloads. Any question here? Okay, I told you earlier, there is no direct communication channel between DPUs, even if they are in the same chip. You cannot communicate data directly in this generation of the PIN architecture. You cannot communicate data directly from one DPU to another DPU. So what you need to do is to communicate through the host with DPU, CPU, and CPU, DPU data transfers. And depending on the workload, you might need to use more or less of these intermediate data transfers. It might turn out that you only need to transfer partial results to obtain the final result on the CPU. In that case, you only need DPU to CPU transfers. Imagine that you are, I don't know, like computing a reduction on all the DPUs in the system, and each DPU obtains a final value that is a partial sum, right? And at the end, what we want is a single value for the whole system. So the partial sums from each of the DPUs are moved to the host CPU. The host CPU performs the final reduction, and that's it. It obtains the result. Well, in this case, we only need DPU to CPU transfers. In other cases, and I mentioned earlier iterative algorithms like machine learning training, for example, we will have to move intermediate results after each training iteration to the host and then probably redistribute those intermediate results for further computation to the DPU. So in this case, we will have transfers in both directions, and we can expect more overhead in our programs, right? Yeah, one question here is how fast are these data transfers? Oh, by the way, right before we go with this, I would like to show you indeed the draft of the lab, because you're going to have to work. I hope people can see it in Zoom as well, because you have to, you will have to work with these transfers. This is more or less how it looks. It's not the final version, so that's why it's not released yet. We are still polishing the draft, but I want to use the current draft for you to become familiar with the lab as soon as possible, and this way, don't panic the day that you start by yourself. So after a short introduction about the architecture, there are not many details about the architecture here because you have them in this lecture and also in the papers and also other lectures that we have given earlier. First thing that you have to do is this task 1, where you are going to experiment with the different data transfers. All types of data transfers between the host main memory and one or multiple Mram banks. So this is serial parallel broadcasts, and both from the main memory to the Mram banks or vice versa, right? Why do you need to do this? Because you need to get familiar with how how the APIs look, right? And how to use different parameters in these APIs, right? Unfortunately, because you are not going to work, at least for now, with the real system, it makes no sense to measure the time needed for these transfers, calculate the bandwidth, etc. Because in the simulator, it's just a functional simulator, so it doesn't really have a model of these data transfers, a performance model of the data transfers, and you cannot see by yourself how fast these data transfers are in existing system, but at least you will get familiar with this pretty quickly. By the way, to do this, you will be given a template. Observe that there are indeed 2 templates. One is for task 1, the second one is for task 2. We can talk about it later, but both folders are indeed organized in a similar way. You can see that there is a folder for DPU code, a folder for host code, and then some support folder. If you look at the DPU code, for example, this one, the kernel itself, the kernel itself is here, is this main function. Observe how we are using already a Tasklet ID. This is the ID that identifies each of the threads. We can even print it if we want. This part, you can ignore it for now. You will find it in your template. And then nothing happens, right? Simply returns. So the code is completely empty because here, in this first task, we only want to evaluate the data transfers, okay? Then if we look at the host code, again, you don't have to probably, you probably don't need to check all the different details, but many of the things that are here you're already familiar with. For example, the path to the binary after compiling this binary somewhere in this bin folder, and you will use it to load it. This is just one function to create an input. In this case, all values are equal to 1 or random or whatever you want. And then this is a function that is in another file. This input params is here in this params.h, is just for the input parameters. In principle, you don't need to change anything here. Just the input parameters, for example, and you will provide them through the command line. For example, the input, the total input that you want to transfer from the main memory to the PIM-enabled memory to the multiple DPUs. That's why we also have some code here to divide the whole input by the number of DPUs. So in the end, there will be one part of the input that goes to each of the DPUs, right? And more things that you can already recognize: DPU alloc, DPU load. They are more or less always the same. So basically, you will copy from one code to the next code because there is not much difference between them. Then we have input and output allocation in the host memory. We create the input here, and then this is where, well, there is this loop just to perform multiple iterations. If you want to repeat the experiment multiple times, in principle, this will just run once. And here you have some timers that would be useful on the real system, not in the simulator, as I said. And then this is where you have to insert code for serial, broadcast, or parallel transfers. So this is more or less how it looks. Anyway, you'll have time to deal with this by yourself. Okay, so but anyway, it's important and interesting, useful to know, especially because many of you are worried about this overhead of transferring data from the main memory to the beam-enabled memory. So it's good to know how fast are these data transfers in this current system, okay? By the way, before I show you the results that we obtain, let me very quickly go back to this slide. UPMEM DIMMs coexist with regular DIMMs in this dual socket system. There are 2 memory controllers per socket and 3 channels each, 2 conventional DDR4 DIMMs on 1 channel of 1 controller. Is this a fixed decision? Is this what we are going to find in all PIM systems? Is this what we are going to find in all UPMEM systems? Not necessarily, right? The way that UPMEM themselves configure this server was to have first, I mean, this is my guess of why they configure this in this way. First, to have enough main memory, right? Because it makes sense to have at least 32 gigabytes, 64 gigabytes. That's normal in any desktop or servers may have more, but that's something reasonable. Let's say 64 megabytes. So I still need to have a few DIMMs of main memory. And at the same time, I want to maximize the number of UPMEM DIMMs, right? Because if I maximize the number of UPMEM DIMMs, I maximize this and I maximize that, right? I will have a more powerful system. But both DIMMs are connected to the same processor, right? Are connected to the same CPU. So you can potentially change the ratio of PIM-enabled memory and conventional memory. And why I'm saying this? Because in the experiments, in the results that I'm going to show you next, what we are measuring is the time needed and the bandwidth that you can achieve when moving data from here to here and from here to here. So depending on how many memory channels you use here and how many memory channels you use here, this time for the total amount of data that you transfer might change, right? And what that means is that the results that I'm going to show you are just the results for this specific system. They could look different in other systems. And it might make sense, for example, that if in my system, I want to execute workloads that need more data movement than others, I may prefer to configure this in a different way, right? And what I'm also trying to say is that the experiments and the results that I'm going to show you don't need to be so significant. It's important as a first approach to understand what of the data movement bottleneck still remains, but is not, let's say, an inherent characteristic or something fundamental to the PIM architecture itself. Okay? Well, yeah, let's go to the thing. We create a micro benchmark to measure the sustained bandwidth for all types of CPU, DPU, and DPU, CPU transfers. And we ran 2 different experiments. You could run different, more experiments, of course, if you want. But here we have 2 different experiments. The first one targets a single DPU. The second one targets an MRAM bank. Remember that each MRAM bank has 64 DPUs and 60, no, sorry, I said, one rank has 64 DPUs and 64 MRAM banks, and that's what we test. If you run the experiments on more than one rank, you will see or you will experience channel level parallelism, because one rank is just in one channel, but if you target multiple ranks, you probably target multiple channels as well, and these naturally increases the parallelism and the bandwidth, right? One thing that we can know in advance is that the DRAM, the DDR4 bandwidth itself, what is given by the standard of DDR4, is going to be the maximum transfer bandwidth that we can achieve, right? And actually in DDR4 is about 19 gigabytes per second. And in some of our measurements, we are not too far from that. So in the first experiment, we transferred data. Data transfer size varies between 8 bytes and 32 megabytes. This is the data transfer size in bytes. Remember that we target a single DPU, and here on the y-axis, what you see is the bandwidth, so higher is better. And these are the results for the CPU-DPU transfer. This is in the other direction. And one thing that you can already observe is that larger transfers provide larger bandwidth, higher bandwidth. But it's also true that the bandwidth saturates at some point, right? You can also see that the bandwidth for different directions is different, but this is due to how the runtime system implements these data transfers, details that are somehow oblivious to us at this point. The second experiment is with one rank. Here we try serial, parallel, and broadcast transfers. Of course, when you target a single DPU, it doesn't make sense to try other than serial transfers, or parallel transfers in the end will be serial because it's just one. But now that we target more DPUs, we can try the different types of data transfers. Here we change the number of DPUs between 1 and 64 is the x-axis. In the y-axis, again, the bandwidth. For serial transfers, the bandwidth is constant, regardless of what's the number of DPUs, right? That makes sense, because if I target a single DPU and I transfer this much, I need this amount of time. If I target 2 DPUs, because the transfers are serial, is first one transfer, then the other transfer. So it's twice the amount of data, but twice the time. So that's why the bandwidth is flat. However, we see some scaling when increasing the number of DPUs for parallel transfers and for broadcast transfers as well. Indeed, the sustained bandwidth of parallel CPU-DPU and DPU-CPU transfers increases with the number of DRAM processing units inside a bank. Okay? Question here, does it scale linearly? No, it doesn't scale linearly, as you can see. There are some issues, maybe, with the runtime system that takes care of these transfers and maybe could be more optimized. That's something that we cannot improve by ourselves unless we try to modify the runtime and the driver by ourselves. But yeah, as I said, these are just some experiments to see more or less what's the ballpark that we are working on for different data transfers. The sustained bandwidth of parallel CPU, parallel CPU and DPU CPU transfers is different for the direction due to different implementations, as I mentioned earlier. And broadcast transfers is the red line. As you see in this case, you can obtain significantly higher bandwidth. And also remember that the maximum of DDR4 is around 90 gigabytes per second. So this 16.88 is not far from that. And the reason why the broadcast transfers seem to achieve higher bandwidth than parallel transfers is because we are using a single buffer, right? A single buffer for all DPUs, maybe 2000 DPUs or 64 DPUs, right? So it's more likely that this buffer resides in the cache of the CPU than if you are using many different buffers at the same time. So that's more or less the intuition that explains these different results. There is also one more thing to consider is that may affect the peak bandwidth, maximum bandwidth that you can achieve in the previous experiments is due to the fact that the runtime needs to transpose data from the way that we conventionally lay out data in DRAM chips to what the DPUs need. You guys are already familiar with DRAM DIMMs and how data is distributed over chips. If you want to maximize bandwidth, you want to access all chips, the 8 chips, for example, in the rank at the same time, right? And if you want to read 64 bits from these 8 chips, you will typically read 8 bits from each chip at the same time in the same cycle, right? So we are distributing bits in a horizontal manner over the available chips in the rank. That doesn't work for a system like UPMEM, Why is that? Because each DPU wants to operate on entire words, not just 8 bits that belong to a 64-bit word. No, the DPU wants to operate on the entire 64-bit word. So that's why the runtime system somehow transposes data, this is done by software, before moving the data to the DPU side. And this way, make sure that each DPU has access to entire word of 64 bits, right? This is something that is completely transparent. You don't have to worry about this. I'm just mentioning this for you to understand why there might be, or what might be the reason why peak bandwidth of DDR4 is not obtained in the previous experiments, but this is completely handled by the runtime system. But anyway, I think it's also an something interesting to mention and for you to observe, right? Because in some sense also reveals some of the challenges that need to be solved to integrate a processing in memory system into a real system, right? Processing in memory architecture into a real system. One of the challenges is that we need to change the data layout for the processing cores or the pin cores or the DPUs to be able to operate on the data, right? So this is the challenge, and this transposing library is one of the possible solutions, right? We could also handle things in hardware as well. Indeed, we talk about some transposition unit when we introduced SIMD-RAM. You might remember that there is a transposition unit near the memory controller to do somehow similar operation for SIMD-RAM. Okay, yeah, our codes are publicly available, micro benchmarks are publicly available, so there you are. Now, next thing, we have allocated the DPUs. So now our program can use, let's say, 100 DPUs in the system. We have load the binary. So the program, the kernel that will run on each DPU is moved with DPU load to the instruction RAM in each of the DPUs, and we launch the kernel is the next thing. After, I mean, and we have also transferred the data, right? Arrays A and B from the main memory to the PIM-enabled memory. So next thing to do is to launch the kernel onto the DPU set. Observe that we don't have to say what is the function, what's the kernel that we want to execute, because we have already loaded it into all DPUs. And here we target the entire DPU set with this DPU launch. At this point, the kernel starts running on the memory side. Observe as well that these launches can be synchronous or can be asynchronous. Synchronous means that the CPU waits here until the kernel terminates. Asynchronous means that the control returns to the application, to the CPU thread, and it can perform more computation, other operations. For example, what does the asynchronous execution enable or can potentially enable? For example, task level parallelism, right? Because right after launching one kernel onto one DPU set, I could launch another kernel onto another DPU set. So this way we can enable task level parallelism with asynchronous transfers, not synchronous as in that line there. Or we could have concurrent heterogeneous computation on CPUs and DPUs. So after launching the kernel in an asynchronous manner, the CPU could continue computing something here, right? So those are two possibilities. Maybe you can come up with some other ideas. Yes.
If you want to have the result, then you want to wait for them, then you will why always.
I mean, it has more potential for sure. It has more potential for different possibilities in your code. But as you said, it depends on what you need to compute. Indeed. What you said also relates to a previous question about the whether the data transfers can be asynchronous, because, for example, in other accelerators like GPUs, you can compute and transfer data at the same time. There is a DMA engine over the PCI Express bus. You can transfer data from the host main memory to the memory of the accelerator, the GPU in this case, and at the same time has the GPU threads computing. It's not the case here because of how the system itself is designed, and it's something that is even mentioned in the patent, right? The CPU has to wait for the DPUs to finish the computation on a specific MRAM bank before accessing these MRAM banks again, right? But potentially these asynchronous kernel execution could be useful as well to perform data transfers and overlap computation with communication, which would definitely alleviate the remaining data movement bottleneck that we still have in this system because we have to move data from the main memory to the PIM-enabled memory. But yeah, it's, yes, go ahead. So how do we know when the asynchronous kernel is done? Here you have, there are 2 ways to check the kernel completion. This DPU sync is in GPUs, for example, where the kernel launch is also asynchronous. You can use in CUDA device synchronize. So that would be similar thing. Okay. Okay. So now next thing is, because even in CUDA programming or in CPU programming, when you launch a function, you have some arguments, right, or some parameters that you pass to the function, but you don't see them here, right? How do we have to pass the parameters to the kernel? Well, because the kernel is going to run on the DPU, and the parameters initially are in the CPU memory or are in the CPU registers, for example, that they are with a CPU thread. We need to use transfers again to move the parameters as if they were input arrays. So we can use either serial or parallel transfers, and there is a way of directly moving these parameters to the WRAM, to the working RAM. It says we will introduce it in the next slides. It's true, you have already seen the WRAM in one figure, but not with enough detail. But this WRAM, as you may remember from that picture, is closer to the pipeline, right? So yeah, it makes sense to put the parameters closer to the pipeline because the pipeline, the threads running in this pipeline are going to need these parameters to perform the computation that the kernel dictates. The way we define a memory array, an array in a working RAM that is accessible by the host is by using this host qualifier. The compiler will know that this thing here, this, for example, this array DPU results is in WRAM, but is directly accessible by the host. And the host can access it by using either serial or parallel transfers. So in this case, we refer to these DPU input arguments. So DPU input arguments is the address that we target from the host in each DPU. But as you can see, the syntax is exactly the same. The syntax of this DPU copy 2 is exactly the same as we use for buffer A and buffer B. And if you prefer to use parallel transfers, then you would use the prepare transfer and the push transfer APIs. Okay, so basically it's the same, but the difference is the, say, address or the symbol that we are using to identify the data, the arrays that we copy. Okay, so yeah, let's go back to the vector addition as a running example, because now we are going to start thinking about how to program the DPU kernel itself. And this is the kernel. It's you see, it's a little bit more complete. It has more lines than the one I showed in the template. But yeah, in the end, it's more or less the same. We start by retrieving with this me instruction. We retrieve the Tasklet ID. And now we use this Tasklet ID to access the data that we have to compute. Observe that we are calculating here, we are obtaining some addresses for A and B. remember that we placed buffer A at the very beginning of the MRAM that is given by this, the address of which is given by this MRAM heap pointer. And after that, we place the address B, I mean, the array B, the buffer B. So that's why we are adding this offset here. And then there are more things. So let's go one by one. But for now, you already know what happens with the, where are those arrays that we transfer? Now we have an address called MRAM base address A, MRAM base address B, to access those arrays, those buffers that were transferred from the main memory to the PIM-enabled memory. Now we know how to handle, I mean, how to access them from the kernel itself. So here we have the tasklet ID. This is the size of the vector tile processed by a DPU. So this is the size of the chunk that we have transferred to the DPU. Here are the addresses, as I said, to array A and array B. And here we allocate the WRAM. What is WRAM? WRAM is this SRAM that is for operands that is closer to the pipeline, right? And this is how we allocate a space in this WRAM in order for the pipeline to access that data. It's pretty simple, MEM alloc. So we are allocating two small spaces for chunks of data coming from array A and coming from array B. We are calling it cache A and cache B, but this is not truly a cache. Observe that, or think about how regular caches, hardware caches, operate or are used in CPUs or in GPUs. You don't need to do anything with respect to them. They are completely transparent to the programmer. I mean, of course, you can write your code in a way that it takes more or less advantage of the locality in the caches, and that will have an effect on the performance of your code, but caches are transparent. Here, this is not really a cache. This is called a scratchpad. It's a memory space that we can use explicitly to allocate data that resides for some time in order to take advantage of the locality. Okay, something very similar exists in GPUs. It's called shared memory or local memory, and it's a memory space that is accessible by all threads running on the same core, the same GPU core, and this data in this shared memory or local memory can be accessed by all threads running on that code. So here is kind of a similar thing. Okay, yeah, next thing to do is to distribute the whole computation over the multiple tasklets. And that's what we do here. Observe that there is a base address for each tasklet, and observe that after each iteration, we are updating this byte index. Yes, one second. We are updating this byte index by the number of tasklets and the block size that each tasklet operates on in each iteration. Okay, so this is the whole thing, the whole buffer A that has been assigned to DPU 0, for example. I know that I have multiple tasklets, multiple threads that are going to compute or operate or process this data, right? And I have to partition it and distribute over the tasklets, right? So what I do is I define a block or a chunk of a size, block size, right? And this one goes to tasklet 0, the next one goes to tasklet 1, the next one goes to tasklet 2, and so on. Because the number of tasklets that I have is limited, right? Is typically 12, 16, something like that. The size of the array might be much larger than this block size times number of tasklets. So that's why we need this for loop here. You were going to ask something?
Yes, from the URAM, so the URAM basically not track the cache, but like its function is to have access more complete data, or it's more to have some kind of shared memory in the two tasks.
It's indeed both things. So first of all, it's not a hardware cache because you have to handle it yourself. You have to allocate space there by yourself, but you can call it a software managed cache. And it's a cache or it's a scratchpad, which means that it's closer to the threads, closer to the pipeline. So accessing data there is going to be faster than going to the MRAM, going to the DRAM, okay? So the way that this is written here means that each tasklet with a certain tasklet ID is going to perform the same allocation. So we are going to have as many of these cache A and cache B as tasklets we run, okay? But at the same time, we could potentially, or one tasklet could potentially access the caches of another tasklet. To do so, you just need to figure out a way of sharing these pointers. Like, for example, defining them as a global variable outside of the kernel. This way are going to be visible by, the pointers are going to be visible by all tasklets, okay? No. This is for the same DPU. There is no other way of accessing data if it's not in the same DPU, either in MRAM or in WRAM. Okay? Yeah, those are very good questions. No, I may have said that threads can share memory. Tasklets can share memory if they reside in the same DPU, because as I said, these WRAM arrays can be shared, but not if it's other DPU. That's impossible. So every single address that you have here in this code belongs to either the MRAM or the WRAM of the same DPU. Okay? Any other question? Okay, yes. Yeah. If you don't fit it, it's same as if your shoes don't fit. You cannot use them. If there is any API to retrieve this 64 kilobyte, not that I'm aware of, it might exist, but I don't know. So this is something that hard-coded. I mean, it's probably something that you would need to know a compile time, because I mean, let's assume that in future generations you will have more than 64 kilobytes. For example, GPUs. As I said, the WRAM is kind of similar to the shared memory in NVIDIA GPUs. The first CUDA-capable generation had 16 kilobytes. Second one had, I think, up to 48. Then there have been GPUs with 64 kilobytes of shared memory, with 96 kilobytes of shared memory, and I think that most recent ones have 192 kilobytes of shared memory, right? So based on that number, you will optimize your code in a way or a different way. But if you know on what GPU you're going to run, and that's something that in GPU programming, for example, you can query, you can check what's the GPU generation, the compiler could decide different ways of using tiling, for example, as an optimization, depending on what's the amount of shared memory. Expectedly, we will see the same in this kind of system if someday the 64 kilobytes increase. Hopefully it will increase, not reduce. But I think it's something that is manageable. It doesn't really make sense to know that at runtime. So to even be able to query it from inside because you're compiling it once, right? Okay, yeah, but very good question. Okay, so now, now that we have this external loop to distribute chunks of size, block size over the multiple tasklets, then we have to use those chunks in some way. Well, there is some bound checking here that we can ignore for now, but basically what we are doing is using this Mram read to transfer data from Mram to Wram. So we copy one chunk of L size byte from address A in Mram to cache A in Wram, and from address B in Mram to cache B in Wram, right? Now the data resides closer to the pipeline. So we can compute the vector addition, operating on cache B and cache A. And finally, after we are done, this vector addition function is external. We will see it in the next slide. After this chunk in Wram is done, we can copy the results back to the Mram, right? And then we go to the next chunk of block size, block size that is still in the Mram, right? And continue the computation. So as you see, it's I think it's pretty simple. But anyway, obviously this requires you to read the code more carefully and understand it well. But this is what your lab is about. Okay, vector addition, this is the external function, vector addition, that computes this buffer B and buffer A. Don't get confused with the buffer B and buffer A that we had in the host. Now this buffer B and buffer A are just these cache B and cache A. Okay, so that is this function that we are calling here. Okay, and as you see, it's just sequential code because this is executed by a single tasklet. Every tasklet will be doing the same on its corresponding chunk of A and B, computing the element-wise addition. Okay, what else? The tasklet is a software abstraction of the hardware thread, as you already know. Each tasklet can have its own memory space in Wram, but they can also share the data in Wram by sharing pointers. And these tasklets can also synchronize, and you'll have to deal with these also in the lab as well at some point. You may use mutexes or handshakes or barriers or semaphores. For a description of these, you can go to Wikipedia or to your parallel programming book or to the SDK documentation. For very quick definition or explanation of the three that you are really going to use in the lab. The first one is the mutex, the mutual exclusion. This is just a mutex as you can find them in other programming languages, for example, pthreads. A mutex is useful to define a critical section, a section where only one single thread can be at one time, right? So we lock the access to some part of the code. Maybe there we update common variables, shared variables, etc. And after that, we unlock not more than one thread or one tasklet, in the case of the DPU, can be inside the same mutex. Then we have handshakes. They are a way of moving data from one specific tasklet to another tasklet, or maybe more than one. This is why there are two functions or two APIs. One is to wait, the thread that needs to wait, while the other one is to notify, to let the other thread know that certain value is already generated and it can use it. And then we have barriers. So barriers are just a synchronization point for all threads that are running together in the DPU in this case. Yeah. But as I said, you can find you can find more details and actually sample code on how to use this in the SDK documentation. And in the end, these are pretty normal in parallel programming languages. So you can find for sure good examples on where to use this. Okay, and we are going to use them in one particular task that you will have to do in your lab is the parallel reduction. In a parallel reduction, what we are basically obtaining is just a single value out of a large amount of input values. It depends on how or what computation exactly we apply. In our example here, we are using the addition. So what we will obtain at the end is the reduced sum of all values in one input array called A in this case. So this is the whole array. We are, first of all, going to partition this array over multiple DPUs. We can divide it into equally sized chunks. Each of them is transferred from the main memory to the corresponding MRAM, and then inside each DPU and inside each MRAM we use multiple tasklets, right? And observe that we are assigning this input array in the same way as we distributed buffer A and buffer B for the different tasklets in the previous example, right? So it takes one large chunk to tasklet 0, the next one to tasklet 1, the next one to tasklet 2, and if the array is even longer, then the next thing would go to either tasklet 4 or maybe again to tasklet 0, right? And each tasklet, because in the end what we want to compute is the final sum, and the addition is commutative and associative, as you know, each tasklet can compute its local sum. And then, in this case, we have 4 local sums. So the last thing to do is to reduce these 4 local sums. How can we do it? Simplest thing, we have a single tasklet. Last one, so at the very end, after the 4 tasklets generate their local sum, we can tell tasklet 0, for example, if you are tasklet 0, take these, and these, add them up, and store in the final memory location, right? It's a single thread reduction. And that's indeed what we did here. Actually, this is the code that corresponds to each individual tasklet. As you see, this outer loop is exactly the same as we use in the vector addition code. We are reading from, load cache, right? We are reading from MRAM. One part of array A is copied into cache A in WRAM, and then we perform the reduction. This reduction is just because in the end it's for a single tasklet, so it's just a serial reduction. In this function, we obtain a local sum, and then we can copy this local sum into WRAM to an array in WRAM that is shared by all tasklets. Where is this message array declared for it to be accessible by all tasklets? As a global variable outside of the kernel, right? Outside of the kernel. If you do it inside the kernel with the memalloc that you have seen in a previous slide, it will be local. The pointer can also be shared in some way, but not by default. If it's a local variable, if this message is outside of the kernel, then it will be visible, directly visible by all tasklets. And each of the tasklets have their own position in this array message. So, so tasklet 0 writes in message 0, tasklet 1 writes in message 1, and so on. So after that, we need to synchronize a barrier to make sure that all threads are done with the previous part and make sure that all local sums are in the message array. This message array can be accessed by the single thread, tasklet ID = 0, goes over all the messages from actually it's a reduction, so from 0 to the number of tasklets or from 1 to the number of tasklets and accumulate. And finally, the total sum for the DPU is here in message 0, and we can send it back to the CPU. Any questions here? Is it clear? Okay. Yeah, barrier synchronization, sequential accumulation, and so on. Well, but that's the thing, right? So here we are using a single thread. Is it the best we can do in a parallel system where you have multiple threads? You can run up to 24 of these tasklets in each DPU, but we are only using 1 for this final reduction. This number of tasklets might be 24, right? So there are many values that can be added at once, right? So we could perform the reduction in a different way. We could use a what is called a tree-based reduction. Observe that in this tree-based reduction, what we do is we use as many threads as we can, and they start performing partial sums, right? For example, thread 0 takes element 0 and element 1 and adds them. Thread 2 takes element 2 and element 3 and add them. And then every iteration, half of the threads retire until we only have one last thread that performs the final addition, and then we are done. This is a tree-based reduction. It's using multiple threads, not just a single one as in the previous code. So it's going to be faster, right? At least it has lower complexity. The previous code, if it's a single thread execution, it has a complexity that is O(n). But if we have a tree like this, the complexity is log n. So it's theoretically smaller, right? Yeah, Tasklet is the same as thread, yes. Yeah, it's a Tasklet is the name that software threads receive in the PIM architecture. In this PIM architecture in particular. You can call them PIM threads or simply threads. In this slide, they are called threads because this is indeed coming from a different lecture. Okay, yeah, so we could implement things in a different way. And indeed, you have here the code for a tree-based reduction. Instead of having one single thread here, we have multiple threads, basically implementing what you have seen in the previous slide. This is a tree-based reduction, as you see. So we have multiple tasklets working here. It's only that the tasklets will start retiring depending on what's their offset value, and this offset value gets updated in each of the iterations. So half of the threads retire until we only have a single thread, thread 0 typically, and so on. Because they have to perform partial accumulations here and store in a shared array message that is in Wram, they need to synchronize after every iteration. That's basic. That's something easy. Something easy to understand if you're here, right? This value is computed by thread 2. This value is computed by thread 0, but this value will be computed by thread 0. So thread 0 needs to know that thread 2 is done. That's why we need a barrier here. That's it, right? And that's a way of implementing a tree-based reduction. And there are other ways of implementing tree-based reductions. For example, handshake-based tree-based reduction. In the handshake, we transfer data from one tasklet to another tasklet, which is in the end what we are doing here as well in each iteration. So we could implement this in a different way. You have a question?
Yes. Is there actually a speed up with this on the UPMEM platform, or especially the barrier probably goes down?
I will let you read this paper. I'm explaining the two different implementations. From a theoretical perspective, this should be faster. Okay? Okay, well, you can learn more about parallel reduction. In the end, parallel reduction is parallel reduction. Regardless of what's a parallel matching, a tree-based approach is probably a good approach in parallel systems. And for GPUs as well, this is one of the lectures in the heterogeneous systems course that is about reduction. Probably some of the insights in that lecture are also applicable to the reduction in the UPMEM system. Again, remember that the SDK documentation is going to be pretty useful. Yes. How many tasklets can perform on one DPU up to 24? Yes, actually, we are going to start talking about this right away. How much time we have? Well, we don't have so much time. But for me, we already covered the most important part of the lecture. I already introduced the lab as well. Remember that the goal of this lecture is to introduce the lab and get you familiar with the UPMEM programming. All the details that I'm going to explain starting right from now, there are in different lectures in the PIM course, and I have also delivered some other talks as well talking about this. So everything is already available. You don't really need to know, also don't really need to know all the things that I'm going to explain starting from now, because most of the lab for you is going to be, let's say, it's going to be useful from a functional point of view, because you're going to get familiar with how to program the system. What I will mostly describe in the rest of the lecture relates to performance. Unfortunately, you cannot measure performance in a reliable way using the simulator. So that's why at this point, the most important part of the lecture is already covered for, you know, our goals at the current point of this course. But yeah, still all of this is interesting. We still have 40 minutes, so we'll probably have time to cover most of it, if not all. Anyway, also no rush. I prefer you to understand things as good as possible, and later you can continue learning and expanding by yourselves. So let's start focusing on the DRAM processing unit, and we are going to measure how powerful the DRAM processing unit is in terms of arithmetic throughput or arithmetic operations and access to the two memory spaces that the DRAM processing unit can access, which are the WRAM and the MRAM, okay? So the DRAM processing unit, remember this figure from the patent? Well, if we take a closer look at each of those chips, what we have is the multiple memory banks, multiple of these slices. This M, you already know that is 8 in the current generation, but observe that the patent says M, because this may change in the future and it will be the same architecture. There is the memory bank here, and here you have the DRAM processor with a pipeline and with access to a local memory. This local memory is the WRAM, right? So that's basically what we have there. Here you can see you know, a different representation. Inside each pin chip, we have a control status interface that is for the host to send commands to the DPU to tell the DPUs, launch the kernel, start running the kernel, and there is also a DDR4 interface because the host needs to access data from the MRAM, either in the beginning or at the end of the execution, right, of the kernel. Here inside each of the chips, we have 8 DRAM banks called MRAM, size 64 megabytes, and we have these 2 SRAM-based memories, one for instructions, the other one for operands. This DMA engine is the one that is in charge of executing MRAM read and MRAM write. Remember the code of the vector addition, where we move data from here to here using MRAM read or MRAM write, okay? So what else? And here is the pipeline, right? There are 14 stages in total. We can take a closer look at the pipeline. As I said earlier, the most recent DPUs that we have access to run at a frequency of 425 megahertz. It's fine-grained multi-threaded with up to 24 hardware threads. What that means is that each thread has its own program counter. They all execute the same program that resides in the IRAM, but each thread running on the pipeline has its own program counter. And it's a fine-grained multi-thread architecture. What does it mean? That's something that you can learn by yourself by reading this slide with much more detail, and also watch this lecture from Professor Mutlu from the Digital Design and Computer Architecture course, where he explains what a fine-grained multi-thread architecture is. Fine-grained multi-threading is basically a technique to overlap the execution of multiple threads and hiding data dependencies. You guys have studied what's a pipeline, right? And you guys know that in a pipeline, we have multiple instructions on the fly, right? If these instructions all belong to the same thread, all belong to the same program, it might turn out that at some point we cannot make progress in the pipeline. That's something I mentioned as well when I talk about the top-down approach and this paper from ISCA 2015, where Google analyzed where the cycles of the pipeline were spent in their Google server workloads. You might remember that paper. So there is a pipeline, and sometimes the pipeline needs to stop because we are waiting for data to come from the memory, or because we need to resolve a branch and then we have to, flash the pipeline and start the execution of new instructions, right? So it's not always possible to take advantage of all stages of the pipeline in every single cycle. However, if instead of having a single thread, I have multiple threads, instructions for different threads are completely independent of each other. Thread 0 doesn't need to wait for thread 1 to bring some data to memory, from memory, right? So that's the key idea in fine-grained multithreading. Every single cycle, you start executing a new instruction in the pipeline, but this instruction comes from a different thread. This means that this instruction can start executing regardless of what's the outcome of the previously scheduled instructions, right? Because they belong to different threads or even different programs, right? So that's the basic idea in fine-grained multithreading, and that's what UPMEM folks made use of in their fine-grained multithreaded pipeline. In every single cycle, we will dispatch one new thread, we will fetch one new instruction from the IRAM, and so on. We'll access registers, we'll operate using the ALUs, or maybe access from WRAM, data from WRAM. As you see, this is also done from these ALU stages, or writing back to the register file, or something like that. Every single cycle, the instruction and the thread that is dispatched and the instruction that is fetched from the IRAM belongs to a different thread. That means that we can have all the time the pipeline full. We can make all these pipeline stages productive every single cycle because there is no dependency between instructions executing in different stages of the pipeline. The pipeline doesn't need to stall. That's the advantage of using a fine-grained multi-thread architecture. And this is something that is pretty common and useful in current computer architectures. And indeed, there is fine-grained multithreading in CPUs, in Intel CPUs, for example, or more significant indeed is a fine-grained multithreading architecture of GPUs. GPUs are exactly doing the same. It's only that they work at a different granularity. They don't use individual threads. They use entire SIMD units, typically called warps in GPU architectures. But every single cycle, you start executing, or the GPU core starts executing one instruction from a different warp or from a different thread in this case. So yeah, that's more or less what it is. So this is how the microarchitecture looks, and this is one slide about the instruction set. You can find a lot of details in the SDK documentation. It's a 32-bit ISA, is RISC ISA, a reduced instruction set architecture. Is not RISC-V. Many people ask if this is RISC-V. It's not. This is proprietary from UPMEM. But yeah, in the end, pretty simple operations, as you'll see, and pretty simple instructions. So we were interested in measuring how fast each DPU can be, and that's why we created a micro benchmark to measure the arithmetic throughput. Observe that, well, this is how the actual micro benchmark looks. At the top, you have a simple C code that we write. For every single tasklet, we do something like this. We go over some buffer A that is in, we go over some buffer A that is in WRAM. Remember that we use this memalloc to allocate data in WRAM. And now in each of these iterations, we access one element from this buffer A, we perform one addition, and then we write. That's something that we always do. Operands reside in WRAM. So if we want to measure what's the actual performance of an operation, in this case, the addition, we have to account for the accesses to WRAM as well. And the compiled code looks like this, that you can see at the bottom. For the, well, here is where we initialize the index of the for loop. Here we increment, and here we jump, right? So it's a kind of simple thing. And as you see, the instructions, DPU instructions themselves are also pretty easy to understand. First thing is to access the one element from the buffer in the WRAM. So first we need to calculate the address. Then we use a load word instruction to access 8 bytes. I think in this part, no, it's 4 bytes in this particular example. And then we perform the addition, and then we store back to WRAM. So that's how it is. That's how it looks. It's pretty simple and easy to understand, as you can see. And by using this simple code, we measure the arithmetic throughput. Arithmetic throughput is in the y-axis for different number of tasklets between 1 and 24 for different data types and operations, float, double, in32, in64, and these for different operations, addition, subtraction, multiplication, and division. This is how the results look for addition and subtraction. This is multiplication and division, and this is for the rest of the data types. And there are one first observation here. It's consistent across data types and operations is that the performance saturates at 11 or more tasklets. That relates to the number of pipeline stages, which in reality is 14, it's not 11. The only thing is that it seems that the last three stages of the pipeline can be overlapped with the initial stages for the next instruction of the same thread. That's a specific characteristic of the pipeline. In the end, most important thing to take into account here is that the saturation point, the number of tasklets for which the throughput saturates is 11, and that relates to the number of pipeline stages. There is one more observation here. For example, observe that the throughput for in32 is slightly higher than the for in64, and there is a reason for that. There is a reason on how the 64-bit integer addition is performed. It's basically because of the number of instructions that we really need for each of these operations. And this is the expression that we use to calculate the arithmetic throughput. As you can imagine, it relates to the frequency of the DPU and also the number of instructions that they need for every operation, right? Remember that for one addition, I need to load data from WRAM, I need to perform the addition, and then I need to write to WRAM, right? So that's the number of instructions that I have to use. In fact, you can compare both codes. The code for 32-bit integers, for 64-bit integers is here, and right on the right-hand side, you can see the both compiled codes. This is done with a pretty useful tool that is Compiler Explorer. It's also recommended for you to use in the lab, or it will be. And it's pretty useful, for example, to compare different codes that might be similar, but not exactly the same. And we can understand what are the key differences. And the key difference between the 32-bit implementation and the 64-bit implementation is this add-C instruction. These instructions, the DPU is a 32-bit processor, right? So instructions operate on 32 bits, but we want the architecture to support 64-bit computations, right? So that's why we need add, and then we need this add-C. This add-C essentially, so this one is adding the 32 least significant bits of the values that we have here in R7 and R3. This add generates one carry bit, and this carry is used by this add-C to add the 32 most significant bits of registers R6 and R2, okay? So based on that, we can count on the number of instructions for a 32-bit addition or subtraction is 6, while it's 7 for 64-bit operands. And this is how we can estimate these numbers. These numbers that you see here are the theoretical numbers obtained with this expression at a certain frequency, And they match pretty well what you can see in our measurements on the real DPU. Then another interesting observation is there is a huge throughput difference between addition, subtraction, and multiplication and division. And this is something clearly different from what you can observe on other general purpose architectures like CPUs and GPUs, where ALUs can perform one addition as fast as one multiplication and vice versa. And this is basically because DPUs don't have a 32-bit multiplier. Pretty simple hardware. Remember at the beginning, I mentioned that the DPUs are pretty simple. It was pretty challenging for UPMEM to design these DPUs in the memory, and they did not have time to design a 32-bit multiplier. Time or motivation, I don't know the reason for that. The thing is that there is no 32-bit multiplier, and the way that the 32-bit, the multiplication and the division is implemented is by using bit shifting and addition. It's more or less, if you remember the primary school algorithm for multiplication, right? What you do is multiplying and then shifting and then adding and so on. So that's what the code is doing. And the problem with that is that if you are operating on 32-bit values, it might need up to 32 instructions. There is one instruction that performs bit shifting and addition in a single cycle. That's at least something good. But you may need up to 32 of these instructions. So that's what makes that the throughput drops so much from addition and subtraction to multiplication and division. And it's even worse if you compare integers with floating point. Why is that? Because the architecture supports only integers in a native manner, natively. There are no floating point computation units. So the execution of floating point operations, same as the multiplication and the division, are emulated by the runtime library. If you are familiar with LLVM, the LLVM framework, for example, includes some of these libraries, some of these functions that can be used by a compiler in case that such support doesn't exist natively in an architecture. Okay, so well, this code is also available, and there you are. Now, one more thing is the Wram bandwidth. Now we know how fast this pipeline can be when running multiple threads on it for different data types and operations. Now we want to know how fast it can access data from here and from here, or how fast it can move data between here and here, right? So first of all, we start with the Wram. In this case, it's going to be, well, relatively simple analysis, because as you see, the Wram is accessed directly from the pipeline. So in the end, one access to the Wram is going to be as costly as one operation in the ALU. That's basically the thing. Same as in every single cycle, one instruction retires, so we can say that the throughput of this pipeline is one instruction per cycle. I'm talking about instruction, not operation, right? So one single add retires every cycle. Also, one single load word or store word retires every cycle. So because the accesses to the Wram are down from the pipeline, they basically have the same throughput as the arithmetic operations, well, not the arithmetic operations, the arithmetic instructions that the pipeline runs. Well, so here, in order to analyze what's the bandwidth that we can obtain to Wram, we implement 4 versions of Stream. Stream is a very popular benchmark to measure the bandwidth of a system. There are versions for CPU, for GPU, and for other accelerators. So we created our version of Stream for the DPU. The DPU, the Stream code is very simple, as you see. This is the first version of a Stream is copy. It's just copy from one buffer to another buffer. Another one is add, where it's basically a vector addition, as you see. Next one is the scale. it's multiplying each element of buffer A by a scalar, and final one is triad, right? That is multiplication and also an addition. So based on that, we can see that here, assuming that buffer A and buffer B have, for example, 64-bit integers, right? Every time that we, so in every iteration, we are reading 8 bytes and we are writing 8 bytes to WRAM, okay? Here, we have 16 bytes read, 8 bytes written, and 1 addition. These are similar numbers for scale, and this is for triad. So based on that, we can obtain what's the bandwidth for a stream for the different versions of a stream, as you see. And there is one first observation, is that the bandwidth is also saturating at 11 tasklets, same as the arithmetic operations, right? Why is that? Because the accesses to the WRAM are done from the DPU pipeline. So throughput is the same, as I said earlier. How can we estimate the bandwidth? By taking into account the number of bytes that we read and write and the number of instructions that we need to execute in total for copy, add, scale, and triad that are in the previous slide. So based on that, for example, copy just needs 2 instructions in each iteration. WRAM load, WRAM store, right? But because that's a copy benchmark. If we have, for example, 11 tasklets, that means that we are reading 8 bytes and writing 8 bytes to WRAM. So in total, in 22 cycles, that is what we need to execute these 2 instructions, we are moving all this amount of data. And that's how we calculate the WRAM bandwidth. Bytes times the frequency of the DPU divided by the number of instructions for the specific operation, copy in this case. And if you see what's the theoretical bandwidth, 2,800 megabytes per second is basically what we are measuring as well. And it happens the same, for example, for addition. In addition, we need to load, we need to add, we need add C as well, because we are operating on 64-bit integers, and then we need to store. So in total, we have 5 instructions for this amount of data that we move in each iteration. So that's how we estimate the WRAM bandwidth. So then, yeah, well, those are, yeah, let's say the analysis for scale and add. For the other 2 could be more or less the same. And then one more thing, because in WRAM, we access single elements every cycle. There is no difference between how the accesses are performed. No matter if one tasklet accesses element 0 and then element 1, or accesses element 0 and then element 300. There's no difference, because in every single cycle, you can get 8 bytes from the WRAM. So regardless of what's the access pattern to the WRAM, we obtain the same bandwidth, which is, is one observation in the end. Well, this code is also available. Now, next thing, now we have to worry about accessing MRAM, the MRAM bank, the DRAM bank. You remember that we move data between here and here by using MRAM read or MRAM write. So that's the first thing we evaluated. What's the latency of those MRAM read and MRAM write? And then after measuring the latency, we are going to measure the bandwidth of different types of accesses, like a stream, also strided accesses. A strided access happens when there is a regular or constant distance between 2 consecutive accesses, but this distance is more than once. That's what we call a strided access. And random accesses as well, when the addresses that we access in every single iteration are completely random. Okay, so let's start with the latency. For the latency here, we use different data transfer sizes. That's something that I didn't mention until now. But remember that in MRAM read and MRAM write, we had to say how many bytes we transfer, right? And that's basically what we measured here. What's the latency of transfers of different size, from 8 bytes, that is the minimum, to 2048, that is the maximum. And on the left-hand side of each plot, you have the bandwidth. On the right-hand side, you have the latency. This is how the latency looks, how the bandwidth looks. We compute the bandwidth using this expression here. And one thing we observe is that we can model the MRAM latency with a linear expression. This black line is the linear expression, is the model, and the model is exactly like this. It's completely linear. You don't see a straight line simply because this axis is in a logarithmic scale, right? Right. So, but yeah, it's completely linear, and one thing that we obtain from our measurements is that this beta, well, this alpha is constant regardless of what's the transfer size, and this beta is also constant, but defines the latency based on the transfer size, right? So one thing we observe is that this beta is 0.5 cycles per byte, or the other way around, is 2 bytes per cycle, 2 bytes per cycle. That's the bandwidth, right? 2 bytes per cycle translates into 700 megabytes per second if the DPU runs at 350 megahertz. And that's more or less similar to what we actually measured, right? More than 600 in the best case for the MRAM read and the MRAM write. Yeah, so yeah, observation here is that the MRAM bank access latency increases linearly with the transfer size following that model, and the theoretical maximum bandwidth is 2 bytes per cycle. One other thing that we observe is that read and write accesses are symmetric, more or less same latency, same bandwidth in both directions, and the bandwidth increases with the transfer size. So in principle, a programming recommendation is to use as large transfers as we can, because this way we maximize the bandwidth, and in the end, bandwidth is the key strength of a processing in memory architecture, right? In the end, we place processors near the memory because we want to exploit higher bandwidth and lower latency than the CPU, right? Well, another observation is that the latency is pretty flat between 8 and 128 bytes, and that's because the fixed cost, the alpha, dominates the variable cost. Of course, if this size is small and this is only 0.5, right? Well, as long as this is 80, for example, 80 cycles, it will dominate for certain sizes, right? And one programming recommendation is that maybe it would make sense to even try, maybe you only need 8 bytes. The program only needs 8 bytes in WRAM, but because bringing more is not much costlier, maybe you can bring more to WRAM, and they are already there as you have entire cache lines in a cache, even if you are going to access only a single word in that cache line. Anyway, that's a minor recommendation, let's say. One other recommendation is that the 2048 byte transfers are only 4% faster than 1024 byte transfers. And that's interesting also in terms of how to optimize the code, right? Because in principle, well, you remember, we allocate data. So we allocate certain space in WRAM where we are going to copy the data coming from the MRAM, right? The size of the buffer that we allocate relates to the size of the transfer. Of course, if we want to transfer chunks of 1024 bytes, we will need to allocate 1024 bytes in WRAM. Or if we want to allocate, we want to transfer 2048, we will have to allocate 2048 in WRAM. But if you allocate more WRAM, you are consuming more WRAM. And there is a limited amount of WRAM. You can make numbers by yourself. If you have 64 kilobytes and you are allocating 2 kilobytes per tasklet, and then using 16 tasklets, that means that you are allocating in total 32 kilobytes. And that still fits in the WRAM, which is of size of 64 kilobytes. However, if you need to allocate 2 buffers and 2 the two buffers are of size 2048 or 2 kilobytes, that means that you need twice the amount of WRAM in total, right? So it might turn out that there is not enough WRAM for the tasklets that you want to run. And if that happens, then you cannot run the program. You will need to use less tasklets or less WRAM per tasklet. Make sense? So that's something important to take into account when optimizing code as well. There was originally one part in the lab that is about, kind of repeating these experiments in some way for you to check by yourselves. But one problem we have is that my computer is not charging. One problem we have is that the simulator is functional, right? So the measurements are not going to be meaningful at all. But yeah, anyway, you can read the slide more carefully and read the paper as well to understand much more of this. Okay, what happens with the stream benchmark? Remember, you're already familiar with the stream benchmark. We use it to measure bandwidth. We first use it to measure the bandwidth of WRAM. Now we measure the bandwidth of MRAM. For copy, we can have two different implementations. We have two different implementations indeed. Let's say the default copy is using MRAM read to move one chunk of data between MRAM and WRAM, and then performs this streaming access, the copy in WRAM with the buffers, and then writes back. The other version saves this inner loop here. It's just reading one chunk, writing the chunk back, right? So there is no access to the WRAM other than the access needed for the MRAM read and the MRAM write. And they perform differently. They have different behavior in terms of bandwidth. The first one that we analyze here is copy DMA. So this is only MRAM read, MRAM write, right? And you can see something interesting here is that the bandwidth here saturates at 2 tasklets. Why is that? The reason for that is, well, there are two reasons for this. The DMA engine can only sustain one access at a time. The DMA engine that sits between the MRAM and the WRAM and moves data from here to there can only sustain one access at a time. So peak bandwidth should be expected to be with just one tasklet. The fact that you have more tasklets doesn't mean that you can exploit more memory level parallelism. There is no such thing here because the DMA engine can only access, can only perform one access at a time. The only thing why we see that the bandwidth for 2 tasklets is slightly higher than for 1 tasklet is because if there are 2 tasklets, there is always one request, one access ready for the DMA engine to get it, right? That's, it's a kind of minor observation, but that's what explains that for 2 tasklets, the bandwidth is slightly higher. So what happens with copy, add, scale, and triad? There is something interesting here. Remember in the WRAM experiments, performance bandwidth saturated at 11 tasklets, and we say that makes sense because the WRAM accesses happen from the pipeline, and we already know that the pipeline saturates at 11 tasklets. But it's not the same for this copy and add. They saturate at 4 tasklets and 6 tasklets respectively, while scale and triad, remember they have more computation because they use multiplication, they saturate at 11 tasklets. And the reason for that is because this is a fine-grained multi-thread architecture, right? You are executing instructions in the pipeline from different threads, and when one thread is not in the pipeline, it's because it's going to the MRAM, it's bringing data from the MRAM, either with an MRAM read or writing data to the MRAM with an MRAM write, right? So in the end, we have 2 latencies here. One is the latency of instructions in the pipeline, the other one is the latency of memory accesses, copies between MRAM and WRAM, right? Well, depending on which of these latencies is larger, we will hide the memory accesses with the execution on the pipeline, or the other way around. In very simple workloads like copy and add that have very few instructions to execute in the pipeline, copy has no instructions other than the WRAM accesses, and add has only one addition per element accessed. There is very little computation. So it's normal that the pipeline the memory latency hides the pipeline latency. And that's why the saturation point happens with less than 11 tasklets. However, for something a little bit more complex, like a scale and triad that need multiplication, and remember that multiplication is pretty costly, up to 32 instructions or up to 32 cycles, performance saturates at 11 tasklets. So this allows us to distinguish between what we call memory-bound workloads, because the performance is determined by the access to the MRAM, and compute-bound workloads because their performance is determined by the execution of instructions in the pipeline and the pipeline latency. Okay, yeah, we have many more results here in these slides. The first one, so the next ones are about the strided and access patterns. I'm not going to explain this in detail. I'm not going to explain this at this point because we only have 5 minutes left. So this was expected. But yeah, you have here also the micro benchmarks that we use for random and strided accesses, and the bandwidth that we measured for. You see different strides here, different strides, and also for the random access, and there are many different observations as well. The lab that you are going to start working on soon has relatively simple codes. You don't have to worry, for example, about, for now, you don't have to worry about the strided accesses or random accesses. There is nothing like that. But yeah, this is, I mean, this might be useful to know for you if you keep working with this system in the future as well, right? Or you go beyond the lab itself. The lab, as you will see, has also extra credit or bonus points. So parts that are not mandatory to do to get the full grade, you can get even more. And as bonus, we can have many different things, because let's say that the range of optimizations that can be done on the extra credit is pretty ample. So you can continue going further and learning as much as you want in this lab. There is also one more thing. It's the first time we release this lab, so you are going to be the first ones to do this lab. You might find issues with that. That's perfectly fine. You have a way to communicate with us. There are office hours. You can use Moodle. If needed, we will do corrections. That's not a problem. Same as if really needed, we will provide you with the feedback that you know that you need to complete the lab. But hopefully you won't need so much. I don't think it's going to be extremely challenging. It can become more and more challenging if you work on the extra credit, and because there is no limit. Let me know your questions. We still have 3 minutes. I guess everything is super clear. Well, as I said, for me, the most important goal of the lecture today was to introduce the programming model. I think that must be clear so far. How you are already familiar with the architecture as well. I think it's more than enough what you know already about the architecture, about the DPUs. We don't need to go into many more details. We may continue with this lecture in a future lecture. I don't know. That's something we will see. For now, you are, let's say, all set to start working on the lab. Regarding comparison to CPU and GPU that you guys asked in the very beginning of the lecture, it's here at the very end of these slides. And And you can watch the other lectures that are recommended from the PIM course, where we go into a lot of detail over all of these. And and also, if you want to see what are the workloads that we identified as more suitable for this specific PIM architecture, and it's something that may change in the future as well, as this architecture keeps improving over time, same as other architectures, x86 or GPU architectures have improved over decades. Nothing else? No burning questions? Yes. Yeah, exactly. That, remember that there are two approaches: processing using memory, processing near memory. This one is processing near memory. Yeah, I call it PIM more generally, right? Same as I can call a CPU or a GPU, I can call both a processor, even though they are different. Okay. Anything else? How to compile? Yeah, I explained that. Yes, there is a simulator. You will receive instructions in the handout of the lab. You will receive instructions on how to use the simulator. Okay. Okay. Thank you very much, everyone. Thank you for staying here for 3 hours of or almost 3 hours of intense explanations. I'll see you in an upcoming lecture.